Example 1.1. How many water molecules are there in your body? Assume that you are nearly all water. B. How many drops of water are there in the oceans of the world? And then C. Which one's larger, the number of water molecules in your body or the number of water drops in the ocean? So starting off with our first piece here, we're asking this question. We're asking, how many water molecules are in Carlos's body, where the mass or the weight of Carlos times G is about 230 pounds. And then that tells me here is that I'm going to approximate that the mass of Carlos is about 100 kilograms. And again, this is assuming that this is all water. It's an approximation. So we can calculate the number of water molecules using two steps. The first step that we're going to do is that we're going to calculate the number of moles. For Carlos. And the way we do that is that the number of moles is typically the mass of the sample divided by Avogadro's number. But in this case, this is going to be the mass of Carlos divided by, again, oops, I made a mistake down here. It's the molar mass. But in this case, it's going to be the molar mass of water. And now that I have the number of moles that are in Carlos, I can use n equal to the number of particles in that sample divided by Avogadro's number, which is also the same as the number of water molecules in Carlos times the number of moles times Avogadro's number. So you could see here that really the big deal is calculating the number, the mole number. Okay, so here we go. So now let's go through our process. So now what we need to do here is that we need to estimate the number of moles in Carlos. Right, so that's the first thing that we got to do. So let me bring this up here. So when I look at this thing, we could see here is that the number of moles is n, so it's going to be the mass of Carlos divided by the molar mass of water. So let's go do that. So what I'm going to do here is that I'm going to use the periodic table. So let me move this over here. I'm going to move this over here. And what I need to do here is that I'm going to calculate the molar mass. So I'm going to use the periodic table to get the molar mass of water. So the first thing I'm going to do here is that from the periodic table, you can see here is that I got hydrogen. So now what I'm going to do here is that I'm going to now put in oxygen. And what we're really paying attention to is these numbers right here. So this guy, the mass, I'm going to approximate that to exactly 1, and I'm going to approximate that to 16. So I'm looking at the atomic mass number to do that. So now the molar mass of water then goes like this. So then the molar mass of H2O, so that means here this has to be the mass of oxygen plus 2 times the mass of hydrogen. And so this tells me here that this is going to be what? Oxygen is 16, so this is going to be 16 grams per mole plus 2 times 1 gram per mole. And then if I convert this, this is not converted yet, but this will be 18 grams per mole, but that's not in proper units. So this has to be 18 times 10 to the minus 3 kilograms per mole. And this is the molar mass of water. So now I have the molar mass of water. So from this, I could now go and compute or estimate the number of moles that are in me. So then the estimated moles of water in Carlos is then going to be given by this here. So it's going to be N times the mass of Carlos divided by the molar mass of water. So then if I start putting in my numbers, this is going to be 18 times 10 to the minus 3 kilograms per mole divided into 100 kilograms. And you can see right away that the kilograms are canceling, leaving only moles. So then I'm going to say that this is about 6,000. So this is going to be what? Averaging this to 18 to 20, this will be roughly about 6 times 10 to the 3 moles for Carlos. So now I have the number of moles. So then the next piece here, I could then go in and calculate. So now I could now estimate the number of water molecules. So then what we'll do here is that we use from the definition of the mole, then this tells me here is that then the number of water molecules in Carlos is going to be the number of moles times Avogadro's number. So if I start to look at this thing, this is going to be roughly 6 times 10 to the 3 moles. Then Avogadro's number is 6 times 10 to the 23 molecules per mole. And again, you could see here is that I get a cancellation of the moles now. And this will be approximately, instead of 36, I'm going to go to 40. This gives me 4 times 10 to the 27 H2O molecules. And this is the the estimated number of water molecules in Carlos. And now let's go to B. So they're asking how many drops of water are there in all the oceans of the world? And we know that the mass of the oceans is 10 to the 21 kilograms. That's just a Google search. So now here I am. So now I'm on part B. And in part B, we want to calculate the number of water drops in all the oceans of the world. So what we'll do in this case here, what we're really looking for is that we're saying that the number of drops in the oceans should equal, it should be the mass of the ocean divided by the mass of a water drop. That's how we're going to compute that. So since we already know that the mass of the oceans is 10 to the 21 kilograms, our whole goal here is to determine the mass of a drop. So you could see that the goal is to determine the mass of a water drop. That's what we want to do. So what we'll do here is that let's use a two-step process. So let's use a two-step process. So the first thing that I got to do is that I have to estimate the size of a water drop. And from that size, I could then use the mass density to actually compute that. So then what I'm going to do here is then I'm going to use the mass density equation, which then tells us here is that the mass of a drop should be the density of water, which is fixed, which then tells me that this is going to be the volume of the drop. So by getting the size of a water drop, I could calculate the volume. From the volume, I could get the mass of the drop. So here we go. So the first thing that we got to do here is that we'll start with the question and ask, what is the size of a water drop? So you want to make it easy. This is a guess. So when I'm looking at a water drop, I'm kind of guessing something like this here. So I imagine that I have some water drop right here. And so what's a reasonable guess for the diameter of a water drop? Right? What's a good guess for the diameter? Well, I want to make it easy. And remember, this is an approximation. So what I'm going to do here is that, of course, the radius is 2 times the diameter. So to make everything nice and easy, I'm going to say that the diameter is about 2 millimeters, which then tells me that the radius R should be about 1 millimeter. So look how easy I tried to make this here. Right? It's an approximation. So now what I'm going to do here is that I'm going to use the mass density equation to get the mass of a drop, where the density of water is 10 to the 3, 1,000 kilograms per meters cubed. Uh-oh, I didn't calculate the volume. Okay, so we'll just put it in our equation here. So then here we go. So I know that now that the mass of a drop should be the density of water times the volume of the drop. But if it's a spherical drop, it should be the density of water. And then the volume of a sphere is going to be 4/3 pi r cubed. So now I'm going to put those values in. So what I'm going to see here is that then this number then becomes what? 1,000 kilograms per meter cubed. Now I need to put the radius into units of kilograms or meters, excuse me. So then I'm going to multiply this quantity times 4/3 pi, and then 1 millimeter is the same as 10 to the minus 3 meters cubed. And you could see here is that one I have in the numerator, one I have in the denominator, and they cancel out. So if you compute this number, then I'm going to get a value of approximately 4 times 10 to the minus 6 kilograms for the mass of a drop, a single drop. So now I have my mass. So now let's calculate the number of drops in the ocean. So now the number of water drops in the oceans is this here. So it's going to be the mass of the oceans divided by the mass of a drop. So this should be 10 to the 21 kilograms divided by 4 times 10 to the minus 6 kilograms. So if I approximate this thing, that's about 1/3 into 10. So I'm going to say that this is approximately 3 times 10 to the 26 drops. And so this is the number of drops. So now if I compare these two quantities, probably a better way to write this thing here is to write this as n, the number of drops. That seems like a little bit more realistic language here. So now, comparing these two numbers, we have the following thing. We have the number of drops, the number of water molecules in Carlos's body. We saw that that was equivalent to 4 times 10 to the 27. And then I'm going to look at the number of drops in all of the oceans. And we see that this is approximately 3 times 10 to the 26. And you can clearly see that the number of water molecules in Carlos is larger, slightly larger than the number of drops in the ocean. So what this is telling us is that there are slightly more water molecules in Carlos's body than drops in all the oceans of the world.